Good morning and welcome you all to the NPTEL course Advanced Distribution System Analysis and Operation. We are at the module 2, which is DER Integrated Distribution Network Modeling, and we have seen the overall architecture or few components how they are operating in the distribution network in our last class. So, today we will continue with the modeling and operation of the DERs, that is the most major component in our distribution network as far as the modern distribution network is concerned. So, we mentioned in the last class as well that what are the DERs? DERs are a small scale energy asset that is used for generating, storing and consuming energy at the local user level. Okay. So, depending upon that, if you see the generation, then you have solar PV and wind. If you see the storage, then mostly the battery sub technologies, and as a load mostly we have electric vehicle. So, we will focus on the mathematical model and the operation of this 4 DER components. So, first start with solar photovoltaic power generation. So, majorly solar photovoltaic power generation is done with a PV panel. So, what are the component or what are the metal we use for PV panel? So, that is mainly your silicon, which has the atomic number of 14. That is the major contributor for the PV panel procurement or fabrication. So, if you see, if we all know that for a atom, your nucleus will have your proton and the neutron, and surrounding that you have electrons, they are surrounding the nucleus and in an orbit. So, as far as the chemistry is concerned, you have maximum 2n square number of electrons at every orbit. If your orbit number is 1, that means your n equals to 1, then you can have maximum 2 electrons in your orbit. If you have n equals to 2, then you have maximum 8 electrons at your orbit number 2. So, 14 means your 2 plus 8, it is 10. So, at the third orbit you have 4 electrons. So, that is there for a silicon group 4 element. You have 4 valence electrons or free electrons are present. So, generally this silicon atoms, they stuck or they make a crystalline structure with their neighboring atom by making a bond with this free electrons, and then you have each electron will have an 8 number of electrons, each silicon atom, and then your silicon structure will be tightly bonded and it is stable configuration. So, at a room temperature your silicon is a very poor conductor. Now, we have to make it a conducting material. So, how to do it? We will dope that silicon crystal. So, that doping means you will add an intentionally an impurities or dopants to a pure silicon to modify its electrical properties. That will convert it into a semiconductor. That means from an insulating material it is now going as a semiconducting material and with a controlled conductivity. So, this dopants, like which kind of doping you are using to increase the number of charge carriers. Let us say if your charge carrier is electron, then you have to make an N type doping. If your charge carrier is hole, then you have to make a P type doping. So, for N type doping mostly we use phosphorus, arsenic and antimony. That means, as I have mentioned that at the outer orbit of the silicon you have 4. Similarly, phosphorus atomic number is 15. So, it has actually 5 electrons at its outer orbit. So, that means if you dope, let us say this silicon atom with a phosphorus, then it will come here, it will make the bond with the neighboring silicons, but 1 electron will be free, that is not having any bond. So, that means that will act as a free electrons and that will act as your majority carrier for N type doping. Similarly, For p-type doping, we use group 3 elements like boron, gallium, indium and others. So, boron, the atomic number of boron is 5. That means it has 2 electrons at its first orbit and 3 electrons at its second orbit. So, if you dope your silicon atom with a boron, let us say this is targeted and you make it replaced with a boron, then what will happen? This bond is fine, this bond is fine, this bond is fine, but the fourth bond you have no electrons for making that bond. So, that means you are creating a space. That space is called a hole, and that hole actually it traverses through the silicon atom. That means this time now it is with this boron structure. Now, after some time this will be here, sometime this will be here, sometime this will be here, because always electron has a tendency to make a strong bonding. So, if you do not have bonding, it will try to go to the neighbor one. So, the hole will move from one bonding to the other bonding. So, that is how your carriers in a p type, that is a hole that flows. We call it as a flowing of hole. So, with this architecture, with this N and P type, we make them as a semiconducting device by reducing the gap between the valence band and the conduction band. We know for the conducting material this gap is very small, but for the insulating material this is very huge that your electrons cannot even go to the conduction band, and for semiconductor it is around 1.107 electron volt. So, only your electrons can conduct when it is at the conduction band and your holes can conduct when it is at the valence band. That means, for making electrons flow for your conducting material, your more amount of electrons must be there at the conduction band. If they are at the valence band, then it is an insulating material. Okay, that means it cannot cross your valence band energy and take that much of energy to go to the conduction band. So, if you see the N type and P type architecture, you can see the Fermi level, which is actually the energy level of the electrons at the 0 degree centigrade, 273 Kelvin. Then you can see that it is conduction band, close to the conduction band for N type and close to the valence band for P type material. Now, you want to make a PN junction for making a PV panel. If you make a PN junction, then Fermi level will become constant. You will not have different Fermi levels. So, to make that Fermi level constant, you have a bend at the PN junction level. Okay. Where at the P type your holes are at the close to the valence band, at the N type your electrons are close to the conduction band. Now, at the normal operating condition, if you want to make this silicon, doped silicon to be conducting, what you want? You want a flow of electrons or flow of holes, whatever. But if you see that in normal conditions, this electrons and the holes cannot flow. That means your holes cannot go down from the P type valence band to the N type valence band, and your electrons cannot climb up from N type conduction band to the P type conduction band. So, the path is blocked, you will not get any kind of power flow or current flow. But now, if you have a sunlight falling on the silicon material or the doped silicon material, what will happen? If the sunlight energy or the photon energy is enough or very strong enough, then it will knock out one electron from the valence band to the conduction band for both the P type and N type. That is from the silicon structure. So, if this is there, then what will happen? So, you have a free electron here, you have a free hole also here as well. Okay. So, you have created a electron hole pair. Now, this electric field of the PN junction, because now you have a free electron and a free hole, that means a positive and a negative field has been created. So, that field at the PN junction pushes the electrons towards the N side. That means, this electron which is at the conduction band of the P type, it can slide down to the N type, and the holes that will climb up to the p-type. So, if these things happen and a large amount of electrons and hole pairs are created at the n-type and the p-type, then this concentration will create a voltage difference at n-type and p-type side. And if you add a charge collector and connect that circuit through an external electrical loads, then you will get a flow of current. That is your flow of current, and you will generate a DC power, because always your flow of hole to this side and flow of electron is at this side. You have no other options. It is not even happening that sometime it is going from this side to this side and sometime it is going from at the opposite side. It is never going to happen. So, that means you have an unidirectional flow of current. So, that means it is a DC power generated, and each and every solar panel is a very low voltage value. So, normally we connect them in a series or parallel depending upon our wish, whether we want more current or we want more voltage supply. So, this is the overall equivalent circuit of a solar photovoltaic panel. So, you have an N type and P type, PN junction, and you have external loads connected, and you have a constant current, as I have mentioned, that you will get your electrons and the holes, those are constant amount depending upon how much irradiation you have. So, that is why the major current source of PV panel, that is represented as a independent constant current source. Then you have a PN junction. So, you have a diode over here connected in parallel. Now, as always you are creating an electron or a free hole, that means there is a always tendency that they will recombine. So, that means few amount of voltage or few amount of charge you are losing at all the time. So, to represent that, you will put a shunt resistance in parallel with the current source. That means, with the recombination you will lose this amount of current that will not go to the supply or the load. Then you have a series resistance that will imply the resistance of the collector circuit or the other wires you have connected with the PV panel. Then you have the external load connected. So, your IL, whatever current you are getting at the load end, that is actually your total current generated minus how much you have lost at the PN junction, and then how much you have lost at the recombination. This is the total equivalent circuit of a PV panel. Then always we want maximum power from our PV panel, we do not want to operate in a lesser power. So, how to get the maximum power? Now, for a PV panel has a typical characteristics that if you increase the voltage level, that means if your voltage is more, that means you are creating more and more free electrons and holes. So, if your concentration is becoming very high, that means their chance of recombining with themselves is becoming very high. So, if that is the case, then your current at the output level will start falling. So, you have less amount of current at your circuit. Similarly, if your current is very less, current is very high, that means your all electrons are coming out from your circuit, then what will happen? Then you have a very less amount of voltage across your PV panel. So, this is the IV characteristics of your PV panel. So, if you make the voltage level very high, then your current is almost 0. So, your power is 0. If you keep your current very high, then your voltage will become 0. So, that means overall again your power will become 0. So, there is one point where your power will become maximum at a particular amount of voltage and the current. So, that point we have to track always to get maximum amount of power from a PV panel, and that point is called the maximum power point, MPP, and that depends upon your voltage and the current. So, depending upon the solar irradiance, if your irradiance is increasing, that means you are freeing more and more electrons, then obviously your current will become higher and you will get more and higher current. And if you increase the temperature of the circuit or temperature of the cell, then your potential difference or the voltage difference in the PV panel will increase. These are specific features of your PV panel. Now, how you can estimate a solar power generation from solar PV panel? One model is the black box model, that is a data driven black box model. We know we have studied ANN, KNN, SVM, CNN, LSTM, any kind of a AI learning techniques. You give them input, according to the input it will generate the output. You give the historical output data as well. So, that we can follow for solar power generation as well. We can give meteorological data, that means your solar irradiance, solar angle, your temperature, wind speed, humidity and all the other kind of factors. We can give the parameters of the PV panel, that how much it is tilted, what is the rated capacity of your panel, how much loss you are incurring, what is the age or degradation of your panel, those things we can keep or we can feed at the black box model. Then the time and the location, because which time you want to generate your solar power or it is generating. If it is at 12 noon, then the generation will be very high. If it is at 5 p.m. or evening 5 p.m., then your solar generation will be very less. So, obviously, the time of day season, that means your sunny day, if it is a sunny day at the hot summer time, then your solar power generation will be very high. If it is very winter time, that means very cloudy or let us say rainy season, then your solar generation will be less. So, this kind of input information you always have to feed. Then the historical power generation, keeping all these things into consideration. You feed those things in a black box model and you will get your power output. But the problem with this kind of a black box model is that you will not get the relationship between your input quantity and the output quantity. That means you will not get that which quantity is dominating or which quantity is needed. Maybe sometime you do not get a input data and you feed the other input data to that black box model and something else results you are getting. That means the accuracy has fallen down to 50% or 40%. So, this kind of output is of no worth. That means you do not need this kind of an output. So, you have to know the relationship between the each and every input quantity and the output power generation. So, for doing that, you need to extend this black box model as a white box model. That means you have to have a mathematical expression that will give your solar power output or the maximum power point value of your solar panel. So, this is the expression. You can see this A is the area of the solar panel, I beta is your irradiance level at a particular tilted angle of the PV panel, eta panel is your efficiency, alpha is your temperature coefficient which is close to 0.004 to 0.005 per degree centigrade. Then cell temperature, that means if it is at the open ground, obviously the cell will become very hot. So, cell temperature and then you have the your moderate temperature or nominal temperature, that is at 25. So, if you are operating at the 25, then you can see this effect will become 0. So, if your cell temperature is going higher and higher and higher, your PV generation will become lower and lower. So, this is actually your rated power generation, and with the temperature effect you will lose this amount of solar power. That means always high temperature is also not getting good amount of solar power generation. Now, you want to integrate that solar panel with the AC grid, because I have already mentioned that you are getting direct current or DC power from your PV panels. So, now your grid is AC, so you cannot directly connect them. So, you need a mediator to connect that PV panel with the AC grid, and that is done by a PV inverter. So, the purpose of PV inverter is to harvest maximum active power from the PV array, convert the DC voltage panel voltage to the AC voltage level and synchronize the output frequency and phase with the grid of the output of the solar panel. This is the typical PV panel, PV inverter. So, the connection is mainly done that you have a PV module, then you have a PV inverter, mostly it is feeding the active power and it can supply and absorb both reactive power. That means, it can run in a lagging and as well as leading power factor. Then you have loads and then you have connected with the main AC grid supply. The inverter is mainly used to regulate that how much active power you will feed. You may always not need the maximum power, because if your load is less, then you need not to feed maximum power. So, that MPPT algorithm you can put at the inverter level. then obviously how much reactive power you will give to the grid or to the load for giving a voltage profile boost. So, if we do not have that reactive power control, active power control obviously we have to have, but if you do not have reactive power control, then what will happen? This is a typical example of it, of a sunny climatic condition when your solar power generation is very high. At that time, if you do not have any reactive power, then you can see the voltage level is going to very high. That means you will have over voltage issues at your customer end. So, that is not desirable. So, you have to have a reactive power control strategy at the inverter, smart PV inverter level as well. So, what makes your PV inverter smart? You have to have voltage regulation capability, you have grid support capability, and you have system interaction capability. With that voltage regulation, you can do with the fixed inverter rating, you have power factor control, you have volt-VAR control strategies, you have volt-watt control strategy, that means changing the active power output depending upon the voltage, and then you can operate at a fixed voltage level. For bulk grid support, you can have fault ride through, that means a small fault or small disturbance is there, still you will run your PV panel, that it will not trip it down, because if it is tripped, then again you have to connect it with the grid. So, other than that, can we run it for few millisecond or few seconds, that the fault will be removed and then again it will be synchronized with the grid, or it can operate properly. So, that is called fault ride through. Second is the voltage ride through operation, where you have over voltage or under voltage issues for a very short time interval, still you will run your PV in panel with the inverter topology. Then you have frequency and wattage control, because we know that P is depending upon the delta, that is the frequency of the network, means angle, and that angle will give how much it is operating at which frequency. So, if your frequency is dropping, your PF characteristics, if your P is increasing, then your frequency will drop, right. So, with this frequency what control we can do, then with the system interaction we can do the coordination and the feedback. That means, if your system is experiencing one disturbance, that will go to the inverter control, and that control will be adjusted accordingly, that your system will be operating now as a very good condition, or you can come over or go over of this disturbance condition. So, generally we will focus today mainly with this voltage regulation capability. So, we can do this voltage regulation by either doing the reactive power control, or doing the active power control, or doing the voltage control, and that is a typical PQ curve or power capability curve of an inverter, and normally it operates in a 2 quadrant. That means, active power always it has to supply, it cannot take back active power. So, active power is always positive, but your reactive power can be positive or negative depending upon the necessity of the circuit. So, reactive power control you can do by fixed inverter rating, by power factor correction, or maybe you will need a fixed amount of power factor. Volt-VAR control, then active power control you can do with the volt-watt control, and voltage control you can do with the fixed voltage control. We will see one by one. So, first is the fixed inverter rating, where you will keep the inverter rating, that means the apparent power rating of the inverter as a constant, and your output power, active output power is fixed at how much MPPT you are running at your MPPT level, that means your maximum power point level. So, depending upon that, your reactive power will be adjusted considering that maximum active power output and your inverter rating. So, this is called the grid following mode. That means, you are just following whatever is happening, and depending upon that you are supplying your reactive power supply. Then the second mode, that is called the power factor mode, where we regulate the output active power as well and reactive power as well, both will be regulated to get a fixed amount of power factor. That means, that is your requirement for the circuit. You need a fixed power factor for your circuit. So, if your power factor is fixed, constant power factor, then active and reactive power generations are adjusted to keep the power factor constant, depend upon the active power generation, how much active power you are getting from the supply or the MPPT level. Other than that, you can schedule also your power factor. That is also kind of a variation of your fixed power factor, that you want your load to be operated at 0.9 power factor. So, depending upon that, your PV inverter is scheduled to change with the time, that every time if your load is changing, that means your power factor level is also changing. Depending upon that, you can fix the reactive power output, and these are the expressions to modulate or to regulate your active and reactive power output from your PV inverters if you are operating at a power factor mode. Then the next is the volt-VAR control mode, where you will control the reactive power output from your PV inverter depending upon the PCC voltage. That means where your solar panel, solar inverter is connected, that voltage. Keeping that PCC voltage, you will regulate the output of the reactive power output of the inverter. So, if your voltage is very low, okay, so what that time you will give maximum support. So, you will give maximum reactive power output. But if your voltage is now increasing from the minimum to the rated value, then you will linearly decrease the reactive power support, and that is given by this expression. When your voltage is at the rated voltage, that means it is at 1 per unit. If it is at 1 per unit, that at that time you do not need reactive power support. If you give reactive power support, then your voltage will go up. So, at that time your reactive power output will become 0. Now, let us say your voltage has started increasing, that means you are now going to 1.05 per unit. So, now what you need? You want to reduce the voltage level. So, for that you have something or someone to absorb your excess reactive power. So, for that you will now starting absorbing your reactive power from this circuit, and that is done by the smart inverter. So, this is the expression for your reactive power absorption. And then when you will experience over voltage, that means if the voltage is more than 1 per unit, at that time you have to have a maximum capacity to grab maximum amount of reactive power from the circuit, as maximum as can possible. So, then your total reactive power support is minus Q max. So, that is how, depending upon looking at the voltage level, you will change your contribution to the circuit as far as your reactive power support is concerned. Now, again by looking at the PCC voltage, you can control the active power support as well. So, whenever your voltage is in between minimum voltage limit to the reference voltage limit, you will give your maximum power. You need not to think of it. But whenever your voltage will go up from the reference value, then you have to reduce your active power output. Then you have to deviate from the maximum power point operation, and you have to operate in a lesser power point operation, and that is also linearly you can decrease till your maximum allowable voltage. And whenever your voltage will become more than your maximum allowable voltage, so at that time you have to make your solar power generation 0 to avoid over voltage condition. That means you already have more generation than your load. So, you do not need the generation, then you just cut down your solar panel. Then there is fixed voltage control mode, where you will give the setting of the voltage at the PCC level. That means you will keep that PCC voltage constant, and depending upon that you will regulate your active and reactive power output, that the total capacity or the total power output will be lesser than its capacity level. Okay, this is called the fixed voltage control. That means to keep the voltage level constant, you are just modulating your active and reactive power output to get the support from the smart inverters. So, with this, if we see the same example that where we have seen previously the over voltage condition, now if we go with the power factor control on the same date, then you can see that your reactive power is starting now consuming. So, if your reactive power is consuming, that means it is acting as an inductive reactance. So, that means it is now lagging your circuit with a something lagging power factor. So, then your voltage level will start decreasing, and you have a voltage level which is at the permissible limit value. Same thing or better performance you can get whenever you will go shift to the volt-VAR control, because depending upon the voltage you are controlling your reactive power. So, if you are experiencing a very high over voltage condition, then you give a very high inductive load or inductive pretending to be a high inductive load, that you absorb huge amount of reactive power and your voltage will reduce from your upper bound and you will not experience a over voltage condition. So, here you have a concern that how will you determine the size of your inverter, because everything we have seen, it is a volt watt control or volt var control or fixed inverter size control, whatever, your inverter rating is important. So, how will you decide that inverter rating? So, there are two cases you can consider. First case, where you will keep your inverter rating same as your PV panel kilowatt rating. So, in this condition, let us say this is the power capability curve. So, if you want reactive power from your circuit, then you cannot run your active power at its rated value. That means, if your 100 kVA inverter is used for a 100 kilowatt solar panel, but you want reactive power supply, then you have to run the active power output at 90 kilowatt and rest of 43.59 kilowatt maximum you can take from your inverter. But if you run at P priority level, at that time, that means you do not need reactive power that much. So, at that time you can take total 100 kilowatt of output from your PV panel. The second case, which is mostly the favorable case, that you can make your inverter kVA rating more than your PV panel kilowatt rating. So, if your operating power factor is 0.9, then without doing the P curtailment, even you can give 48.18 kilowatt. That means, you give your 100 kilowatt and also you give your VAR support as well. You need only to curtail your active power whenever you need more reactive power. Let us say you need 50 kVA. So, at that time you cannot operate now at 100 kilowatt, now you have to reduce that. So, but that is not much followed in real time. So, mostly this is the favorable inverter size determination process for our real life circuit. So, with this we will end today's lecture and we will continue with the other DER's model in our next class. Thank you.